Thank you all for coming for this one more edition of the workshop and partial differential equation and applied mathematics. That is being a joint effort between many people now. I mean, FRJ, UFI, people at Colombia, Portugal, and Maringá. So it's a great pleasure to have all you here. This is a very special seminar. It's a seminar in honor of our women mathematicians, scientists and mothers and researchers, and it's a really real pleasure to be able to chair the seminar today in their honor. Today we have two very accomplished mathematicians, two accomplished women mathematicians, will give us the pleasure to talk very diverse and different topics. And to begin with, I'll hand up the word to Marcelo, who's going to introduce our first speaker. Thank you, Marcelo.
Okay, thank you, Max. To talk about Irena, some few words. Irena is a very important person in my life.
I didn't know that, Marcelo.
For me, Valeria, and a lot of guys around the world. She's a very special person, really. But because of the time, I would like to read just a paragraph that about Irena Lasiecka. She obtained his MS and PhD in applied mathematics from University of Warsaw in Poland. I not say the year.
Go ahead.
Her research interests include nonlinear PDEs, optimization control theory, dynamical systems, and numerical analysis. She is author of several books and review papers and over 400 original research articles, and more than what I remember, 14,000 citations in MathSciNet, at least. Her first academic appointment was an assistant professor in Polish Academy of Science in Warsaw in 1977. Lasiecka has been affiliated with universities in the United States, the University of California, Los Angeles, the University of Florida, and finally, University of Virginia, where she has been a professor since 1987. Her current position, there is a common health professor of mathematics, a post she has held since 2011. In addition, Lasiecka has held a number of visit positions during her career, both in the United States and Europe. She has supervised about 20 PhD students at least, I count this, and 20 postdoctoral fellows. She has been a chief editor of various mathematical and engineering journals, as well as a leader of several third-party research projects. Lasiecka has been given several awards for her research work. Not recently, but in 2011, she received a prize from Cyan. The Dahlia Prize for contribution to differential equations in control theory. So, just this, I would like to talk about Irena. Irena, go ahead.
Okay, thank you very much for this wonderful introduction that I feel almost embarrassed to listen to. Thank you very much, Marcelo. No, it's very kind of you. The topic I want to talk today about is related to the third order in time dynamics, which is a dynamics which describes nonlinear acoustic waves, and that this is an area that has acquired quite a lot of resonance in mathematical literature recently, not only because of application, but also because of some methods which have been developed in order to study this problem. And my emphasis today is to deal with the dynamics which is impacted by the actions from the boundary, because it has not been much dealt with in the past, and they are new phenomena which I think are of interest. The work I'm presenting is a joint work with Marcello Bongarti and Jose Rodriguez. Jose, you, of course, you know, because he comes from you guys, yeah, from Maringá. And Marcello is from Sao Paulo. So Marcello is graduating this year with a PhD and is joining Weierstrass Institute as a postdoc, and Jose is still in Memphis. So these are co-authors. So let me give a very short overview. Part of my talk is kind of a review of topics, and with some joint new stuff at the very end, which relates to control from the boundary. The motivation for the models comes from all kinds of areas. High frequency focus ultrasound was one probably original motivation when you do medical imaging and you want to focus your rays on a target which has to be somehow diagnosed. But there are also areas of viscoelasticity, thermoviscoelasticity. So there are more and more models cropping in which somehow involve this particular third order in time modeling. And there are two basic models of nonlinear acoustics. The first one is so-called Westerwald-Kuznetsov. And this is a second order model in time of parabolic type, which exhibits infinite speed of propagation. And the second one is a more Gibson-Thompson, sometimes the name of Jordan is added to this name. And this is a third order in time, and it removes the paradox of infinite speed of propagation, which is known for the acoustic waves as not really reflecting reality well. And that, of course, is of hyperbolic type. This is the second type of models that I'll be talking. So what are the issues involved? These are nonlinear equations, so there are, of course, quasi-linear, so you have to deal with the well-posedness, both global and local, okay? Then is an interesting topic, which in fact was a part of a Marcello Bongarti thesis, that what is happening with the model with the relaxation time, which is this parameter tau, goes to zero. So it means that you would imagine that one model like a third order will go to the second order. And there are new interesting phenomena there. And then we want to talk about what happens on the boundary. Since the third order equation is of hyperbolic type, so there is a strong component of a wave equation inside. You would imagine that some of the research which was done for the wave equation, like hidden regularity and controllability, can also be detected for this model. So we see that it's not exactly the same. And by the way, there are a lot of papers floating in the air which provide the wrong results. Okay, somehow people take for granted that this is part of it is wave equation, but the modeling is incorrect. And then we talk about stabilization via friction, memory, and boundary damping. And the last topic is boundary control and feedback control of the model starting from the boundary. So this is a brief overview. So the challenges are several. First of all, we deal with a nonlinear wave propagation. Then we have a singular perturbation problem, because going with parameter of relaxation tau to zero, you go from the generator, which is singular, reaching a parabolic situation. And then, of course, you have a question of regularity when you apply boundary data, which are not smooth, okay? Because if they are smooth, then techniques, old techniques also coming from Lyon's book, okay, applicable, but with say, two boundary data, these are issues. And that's what we'll be talking about. So in part one of my talk, I will first provide a short review of MGT dynamics. In part two, we just discuss effects of the boundary. In part three, I'll talk about feedback synthesis and related Riccati equation, which provide online control for the model. So this is a situation that we are dealing with, classical situations in medical imaging. This picture here belongs to Marcello Bongarti. So you have a lesion here, say in some tumor in some organ, okay, whatever it is, and you want to focus, you want to do diagnosis, so you want to focus ray, ultrasound or acoustic waves by applying some transducers on the external part of the body. So the whole thing is, as you see, strongly focused on the lesion, and you would like to see the propagation of this wave through the body, through the environment. And here it's another example. In fact, it's a control problem that we will be discussing. You have a focal point inside, and you have a transducer here on the boundary. And there is acoustic medium wave propagation inside. So we are focusing signal in such a way to hit this target part. How we are focusing it by applying is a piezoelectric or piezoceramic disc here around, and that will be precisely the area we control. One thing I want to mention is about this problem of interest, of mathematical interest. This is a boundary condition of Neumann type all along, and we are not going to dissipate Neumann part of a boundary. It's just known as one of the difficult situations when you don't have really methods of multipliers or propagation well developed. So we have some results here under convexity assumption. Okay, so regarding the modeling, so all you need to do is just to remember that three equations. The first one is a conservation of mass, so rho is a mass density. V stands for acoustic particle velocity. So that's the first equation. Second equation is a momentum equation. So you see that it's like a fluid, yeah. V being acoustic velocity potential, and capital T, it's a Cauchy-Poisson tensor, and this is a transport part, okay, of a nonlinearity. And the last one, it's an entropy equation, which involves deformation tensor. Quantities to remember are two. Essentially, we will be looking at the equation, scalar equation, in terms of the velocity potential psi, or in terms of the pressure. Pressure is defined as a time derivative times rho density equals a gradient of P. Okay, so P is so we will be working with a P as a variable U. So one thing to keep in mind in derivations that because this is a heat transfer, heat wave, so you have to apply some heat laws, and there are two basic ones, Fourier or Catania. Fourier law just directly relates flux to the gradient of temperature. Catania law accounts for some relaxation time parameter, so it takes time for the heat to reach a given location, as that is reflected exactly by this parameter tau. So if you use these laws, depending which one you use for the Fourier law, you get Westerwald-Kuznetsov equations that you see left-hand side is nothing less but like a classical strongly damped wave equation, but right-hand side has a nonlinearity quite heavy because it's a second time derivative of the square, okay, of a quantities. For more Gibson-Thompson equation, we do have a third order in time with a parameter tau because of the application of Catania law. Here are people who really contributed to the development of this models: Jordan Pedron, Christoph, both Ivan and Christo, also Brian Stroger, and Mario Fabrizio is always of tremendous help because he's a great modeler and he understands mathematics behind very well. So to recapitulate, we have a Westerwald equation which is of parabolic type. So here it's a parabolic type, and there's this coefficient B. B is very important, is diffusivity, and it has to be positive. And there is a nonlinear term. So if you rewrite this equation as a degenerate quasi-linear equation, you can see that what happens at principal part of an operator can degenerate with a solution. Okay, K is a parameter of nonlinearity, and on the right-hand side you have some nonlinear term of a second order. So can be written, can be seen mathematically this way. Laplacian, it's a usual Laplacian, or can be of course more general variable coefficient, and there are boundary condition associated, either Dirichlet, Neumann, or Robin. So this is a Westerwald equation. Now, what do we know for Westerwald equation? We have a global well-posedness. What does global mean? Global means, and this is joint work with Kaltenbacher, going back many years, more than 10 years ago. What does global mean? Is that if you take initial data sufficiently small, and okay, how do you measure smallness? You have two energy functions. Okay, so you see the first one is a classical one, which corresponds to the wave equation, but then you have an extra derivatives in the second part. Okay, so if you take a sufficiently small, then solution exists globally for all time. So it's not only. So the size does not depend on a time horizon. So that's a classical quasi-linear type of a situation obtained by the methods. For the MTG equation, okay, when we have a Catania law and finite speed of propagation, so our equation has an extra third derivative on the left, and the nonlinearity is the same, okay? And then I just want to recall that coefficient B has to be strictly positive, because otherwise even linear model would not be well posed. So it's important to remember that this third order equation might not be necessarily as a linear model well posed unless B is strictly positive. Okay, there's no semigroup. So, but B physically is strictly positive. C square is a speed of sound. Alpha is a parameter of potential dissipation, depends on the material. And here we have this nonlinear terms. Okay, so this is a model. And as we say, that the presence of the third dynamic of a third time derivative is typical in extended irreversible thermodynamics. So it means that precisely we have to account for the propagation of heat waves, which propagate with a finite speed of propagation. And that is necessary to have this tau positive. It gives you a hyperbolic character. It's interesting to note that this case of a nonlinear equation in one dimension was already introduced by Professor Stokes in 1851, exactly in a connection of considering heat waves, propagation of heat waves. So as we see heat and wave together. Okay. Now, to convince yourself that it is really hyperbolic situation, just you look at the spectrum of a linear model, and you see what happens, that you have an asymptotic behavior. So there are two branches which go to this imaginary, not imaginary, to vertical axis, and there is one branch which is on the real axis with a point of accumulation, which corresponds to so-called point spectrum. So this is a typical configuration, and you can see here effects, for example, of diffusivity. So what happens is these branches are going more to the left, so there is like, more damping in a sense, but still goes vertically to the vertical axis of imaginary, on real part negative, okay? And there is a point of a point spectrum, so there are a bunch of eigenvalues converging to this point here. Okay, so this is a typical situation. It is possible that the model is unstable, so you get even a real part of eigenvalues positive, and that leads to some chaotic behavior. And you will see that it depends on the parameters in the equation. So you cannot preclude instability from the equation. And this is all for linear modeling. So here is a nice, normally I would have a movie showing how eigenvalues converge and eventually approach this imaginary axis and accumulate here is a point -5. So you see that it is some sort of a, at the beginning it goes parabolically, but then goes vertically up. Now, one thing, perhaps since I have this picture here up, when we study situation when tau goes to 0, so you have to have a parabolic behavior at the limit. Yeah, you would expect that. So what happens with the spectral analysis? And here Marcello has a very nice movie for this. This vertical asymptote here converges to -infinity. Okay, so does not disappear. Okay, but it converges to -infinity. So it means it is farther and farther away, but it is still there. Okay. And that's exactly a spectral type of a situation. So now let me go back to the abstract formulation for both equations. For Westerwald, Kuznetsov, we have here this degeneracy in front of a second time derivative. For MGT, we have a tau positive, and also degeneracy appears here because solution U is in front of UT. And there is a nonlinear term. Okay, so these are equations to study. And then let me remind you some old results on linear stability. So when tau is equal to 0, and you take linear problem, so we have a strongly damped wave equation. So everybody knows very, very well that as long as alpha, which is damping coefficient, non-negative, okay, then the system is exponentially stable. But when tau is positive, then exponential stability is if and only if we have this value of the parameter positive. So you see, it depends on the relaxation, depends on diffusivity and speed of sound. So alpha alone positive would not guarantee you stability for the linear model. In fact, it can lead to the chaotic behavior. Okay. Now, having these results on linear stability, one can show global solvability for nonlinear system. And we know then when tau is equal 0, so Westervelt equation, we have existence of unique global solution, provided initial data are small, either with respect to topology. So this would be like H2 times H1, or there is a result due to Meyer and Wilke when they go working on LP spaces. And this is W2P, W2P1, okay, for P below, not necessarily up to 2, so there's largest range of spaces. Yeah, now when tau is positive and gamma is positive, so stability parameter is positive, then there exists a unique global solution, provided initial data are small with respect to this triple of spaces, which will correspond to H2, H1, and L2. Okay, so this is more or less situation for the nonlinear with zero boundary data, either Dirichlet, Neumann, or Robin. Okay, so this is all known and situation. Now, let me remind you this parameter of stability, which is gamma equals alpha minus tau c square over b, and that needs to be positive for stability. Okay. An energy function with which we are dealing with MGT are exactly the two. The first one is H1, H1, L2. And for nonlinearity, you have to also add H2 component for the pressure. Okay. And if gamma is positive, you take, say, a linear problem or nonlinear case. For both cases, we do get exponential stability. By using this result, one can show global well-posedness for small data. For small data, but uniform for all times, so they are not depending on times. So now the interesting question that was raised is, okay, so what happens in so-called critical case, namely that this parameter gamma, it's either 0, so we don't have a stability because of a linear model. Just from the modeling, or perhaps it depends on X and you don't have uniformity. That's another situation. Might not necessarily disappear, but might be deteriorated. So here there are couple of ways to proceed. One of them is adding memory damping, and there is a bunch of paper by Italians, De Loro, Pata, also my former postdoc, Xiaojun Wang. I just want to say that here, in case of MGT, memory damping is more involved because it involves kernel which depends on two variables, on a pressure and its velocity. Okay, and in general, if you put only pressure alone, you cannot stabilize exponentially, which is a like wave equation. Okay, so there are a lot of pathologies coming from memory, and one has to be careful in calibrating this linear combination in order to get stability. What I want to talk today is more on a boundary damping. So another way of stabilizing is to put some friction on the boundary and then see what is going to produce. And this is a recent work with Marcello, Jose, and also Roberto. So let me just say a few words about asymptotic analysis when tau goes to 0. So you expect that MGT goes to Westervelt at some point. Okay. So first of all, you have to define a convergence. What does convergence mean when tau goes to 0? Because one equation has 3 coordinates, another has 2 coordinates. So of course you have to take some projections in order to compare potatoes with potatoes. One thing should be mentioned is that here any methods, or even for a linear case of a typical convergent structure cut or related, is not going to work because a generator becomes singular. Okay, so when tau goes to 0. So we have to be careful and essentially work out the estimate, and that was the work of Marcello. So let me just mention here the situation. So the generator for the linear case is very simple, you know, we can just written down. Here is a matrix operator, but there is this factor 1 over tau. When tau goes to 0, this goes to infinity. That's what creates a situation. Problems when you try to deal with a classical convergence of a semi-group type of results. And in fact, the convergence of this dynamics has been also considered by Barbara Kaltenbach and Nikolic in the recent papers, 2020, 2019. And what happened, they were able to show weak convergence, but strong convergence has been left as an open problem. And the reason is that there are some mathematical reasons that I will explain in a moment. On the other hand, there were a lot of numerics which suggested that the result should be true. Okay. And now, what was the main difficulty? One of the main difficulties was that, you know, this is a quasi-linear problem, and in order to get solvability, you need this smallness. Okay? Now, in order to get a strong convergence, you have to have a smallness in the topology, which is even higher than energy space. Okay. And then you would like to somehow to get a strong convergence eventually for the semi-group, you would like to use some density. And density combined with a small ball is not really compatible. And so you cannot do this. So that's a difficulty. So you have to simply rework entirely quasi-linear theory with respect to the topological level and require smallness at a much lower level than it used to be in the past. So essentially the ingredients to solve this problem, to solve this open question, is you have to first of all control singularity of the highest derivatives in tau. It is going to go to infinity, but question is how fast, okay? So you must have an estimate for this. And then the second ingredient is a tightness, reduction of the smallness in such a way that we require smallness only for the very base energy, not a higher level of energy. But okay, you can require, but then you have to also show that this requirement, the smallness, is invariant on the dynamics. That means the tightness on the dynamics. So these are the 3 points, you know, which have to be resolved and lead to the following result, which is joined with Marcello and also Sharon Fon, which is a former student, she already graduated. So the result consists of 2 statements. The first one is a rate of convergence, okay? And I want to emphasize that initial data are assumed to be small in the space, which is just a very basic energy space, okay? So this is the space which is H1, H1L2, okay? It doesn't have the 2 derivatives. However, for rate, but boundness has to be for initial data in a higher topology. So you see a lot of derivatives. And then there exists independent constant T and tau, such that we have a rate of convergence of the third order dynamics projected on the 2 coordinates minus dynamics to Westerwald applied to the projected initial data, okay? So this is a rate of convergence, but to get a strong convergence was essential precisely to make sure that the smallness is only at the very low level. So there is no smallness assumed for the higher derivative. It is a little bit like with the Navier-Stokes equation. People try to not to go to the BMO minus 1 because the smallness in the topology, it's really can still allow large data. So we can still have a large data here. And we get a strong convergence, and this is answering an open question raised in the literature. Now I want to talk about what happens when we put a non-homogeneous boundary data, okay? So what are the questions that one would like to ask? Okay, just following what happened for wave equation in the past. So let's look at this linear equation forced by some function f, and assume that it's 0 on the boundary, and you have some initial data in energy space, say H2, H1, L2. This is a good combination of initial data in line with the third order dynamics. And you ask a question, what happens with the normal derivative? Okay, that's a classical thing like was a hidden regularity for the wave. And a second type of question is similar, but this time you feed also data on the boundary, Dirichlet data. And I took initial data here. I'm taking, as you see, in a lower topology. There's a reason for this. This should be H2 dual, not H minus 2. It's not exactly the same, but bearing this. And you ask a question, what happened with the solution due to original boundary data, and what happened with the normal derivative? So if you do so-called brutal force, so it means you apply interior regularity and trace theorem, the usual thing happens that if I take initial delta in H1, and H1 is H2, H1 L2, yeah. So a solution will remain in the space, okay? That's a right now well-known result. So if it remains in H1, so it means that we have a first coordinate in H2. If you take a normal derivative of H2 function, you get H1 half. Okay, so that is so-called brutal force. And there's nothing hidden here, it's just brutal force. But the question is, can we do better than that? Okay, because that's what one would expect. And the answer is yes, as you will see later. Okay, but to understand this, perhaps let's review very quickly hidden regularity for wave equation, because it helps to see, okay, where is this hidden stuff? It's not necessarily that multipliers are showing, okay? They are proving, but they are not showing much. So if you take a wave equation and you take zero boundary data, okay, and you take initial data in, say, space H1, L2, so classical finite energy space, we know that wave equation remains in H1, L2, okay? Now again, brutal force, if you apply the normal derivative to that solution, so if you are courageous enough to apply trace theorem to H1 functions, which is incorrect, but formally, you will end up with minus half, okay, 3/2 below H1. On the other hand, we know that for this model, we have a normal derivative in L2, so there is a gain of half of a derivative, okay? And this was a result proved with Jones, but also you will see that was even known earlier by methods of looking at a hyperbolic system, which is more convenient here in this case. Now, if you impose boundary data on the boundary and you assume that it's H1, so what happens here, your solution is still in H1, but normal derivative is in L2. So, which means that we have a gain of 1/2 derivative working from the boundary data to the normal. And then finally, if you take a G in L2 only, the solution is in L2, which is already hidden in some sense, and normal derivatives in H minus 1. So again, gain of 1/2. So these are all results known for wave equation. And in fact, they are written here that if G is in L2, solution is of wave equation is also in L2 and normal is in H negative 1. Okay, so, but I want to see this result from the point of view of Fourier variables, to see that it's not really hidden, that it's very predictable, and you don't need any multipliers to understand this. Okay, you just need very elementary calculus. So, and in fact, this was the way that was done in 83 in my joint paper with Roberto, by approaching things from point of view of hyperbolic systems. So if you look at the wave equation, which is forced by boundary data, and say initial data 0, so what do? You do a classical construct. You apply Fourier Laplace transform in tangential direction. Tangential meaning time and space in a tangential, and you solve equation in the normal direction. Okay, so that's a classical PD approach. So if you write for a Fourier transform, Fourier Laplace transform, then you have a second order in X with a symbol which is S squared plus eta squared, which corresponds to the second order derivatives time and space. And then on a boundary, it's equal to G. So for X equals 0, it's a half space problem. So X equals 0 corresponds to the boundary. So we substitute G. You solve the things like, I don't know, in a very first PD course, yeah, undergraduate. And we get a solver in terms of this data and the exponential of this operator here, which is a first order tangential operator. And then you take a normal derivative. So you see at the end of the day, you obtain very nice expression, which is Fourier transform of G okay, which is L2 function. This is Parseval equality, so it's isomorphism, but it's pre-multiplied by this first order operator time and space, yeah, because it's a square root of a squares, okay? So obviously this will be a first order operator, so we'll take you L2 function applied by, followed by first order gives you H negative 1, which is a hidden regularity in optimal, okay? So you see how easy it is to see and to essentially, of course, this is not a proof for any bounded domain, you have to do commutators and all kinds of things, but this is exactly to see that there's nothing hidden that is there, okay? Now, for the Neumann problem, situation is more complex because you can do the same thing. However, we say that the Lopatinsky condition is violated. What that means, or Kreis-Sakamoto is the same thing. And that is seen exactly through the same calculation. So we solve a wave equation, we do Laplace Fourier transform in normal, we solve in X, but this time we have a boundary data on X derivative of a Fourier transform. So we solve this thing. Okay, so we get a square root in the denominator, and eventually your final solution has a boundary data divided by this operator here. Now, if you are not careful, you can say, okay, I have L2 function and I divide by the first operator. Yeah, it looks like a positive. Here, okay, you can add one, not to make sure not to worry about what happened at 0, but this is not essential. It's essential for a large frequency. And then you will get a conclusion that there is a H1 regularity. That will be incorrect because precisely the square root here is not a coercive first order operator. You just write it down in terms of a Fourier transform, and you see that if you look at the so-called characteristic sector of a wave operator, and this applies to dimension 1, 2 and higher, then we have a cancellation between time and tangential space, yeah? So this does not give you a second order operator. Alpha is just a real part, so this doesn't give you regularity. So the only benefit is from imaginary, this I2I alpha beta. So this operator is really smoothing by 1/2, not by full derivative. And that's why we get a derivative on a boundary in H1/2, okay? For the Neumann, not H1 as was believed. And also multipliers clearly show that that's not the case. So in general, just for the record, that when we have a Neumann problem solvable, then the optimal result is not this 1/2 because commutators are going to steal a little bit of more differentiability, but we are getting solutions in H2/3, not H1, and on the boundary 1/3, okay, not 1/2, okay. This is because of the commutators, and this result was proved, in fact, be optimal by Tataru, and there is our paper with Roberto in 1989. So it's not H1, like some people did believe. So there is a hidden gain, but only fraction, and there is, in some sense, loss of 1/3 derivative. You don't get H1 here. But solutions are H1 for one-dimensional domains only. And the counterexample to higher dimensions that cannot be H1 goes back to Rausch in 78. Okay, so this is the optimal situation, and you see that you can get really results from the elementary Laplace Fourier type of argument, and at least to get a feel what we need to prove. I had this thing. There's also something that is not working well. Okay, so now there are, of course, if you look at the wave equation, the optimal results from the boundary can be just the very first line. So you see what happens that first derivatives on the boundary are transported through the wave Dirichlet dynamics without any loss of a regularity due to trace theorem. So trace theorem does not take away half of a derivative. And this is a full statement of the result. If you feed H1 on the boundary, you recover first derivative also on a normal derivative in L2 with a full regularity. And this kind of results now can be proved by PDO calculus, by multipliers, by duality transposition, by semigroup methods, but also by first order hyperbolic system, which is was original way of looking at the problem, and it is very convenient when you look also at MGT. Okay, so I want to perhaps emphasize this. I don't know why this is going me wrong way there when I go from them. Okay. So now we talk about MGT, okay? So what happened here? And that's the same question. So we feed a problem on the boundary with L2 and take zero initial data in order not to have a situation very simple, and function f, say L1, L2, whatever, classical right-hand side. So the first question is, what is the definition of the solution? Okay, and you see that this is not very obvious how to do the thing, because the pattern from wave equation is not going to work. And in fact, as I said, there are some papers floating around with very wrong results, and they are wrong. I will just show here through the counterexample. So to understand this problem, let's look at the completely trivial situation. So you have our generator, which is this matrix 3 by 3. And the scriptates Laplacian, okay? And of course, this can be rewritten as this basic matrix plus P, and P it's a lower order 10 because it contains this derivatives of a lower order. So for regularity purposes, really the very first component is critical to consider. So if you look at this special model, so our MGT becomes, look how simple, with 3 times derivatives of W equal Laplacian of WT, zero initial data and boundary data here. Couldn't be any simpler. So what one would do with MGT, it's a toy that we work all the time with now. We make a substitution in the following way, that you introduce a variable z, which is a time derivative plus this coordinate applied to W, because that reduces to wave equation, at least to a partial wave equation. So you do the same thing for the special model, but the second contribution is 0 because I'm taking c equals 0. So I have just elementary substitution, z equal WT, it's as everybody would think about, and you obtain the following wave equation. Second time derivative equal Laplacian, and on the boundary, it's equal time derivative of G, okay? And we want to think of G as a boundary data. And now we want to look at the regularity of this elementary wave equation fed by boundary data, time derivative. So you take a function which is G identically 1, which is C infinity, couldn't be any smoother. Okay, so smoothness is not an issue. The model is going to be an issue. So what happens if I take function equal to 1, then this becomes 0. Okay, if we have a wave equation fed by 0 with 0 data, then no one will have any doubt the solution must be 0. And you go back to the W variable, which is simply resolving to the integral, gives you 0. So it looks like the boundary data, which are 1 on the boundary here, produce you 0 solution. Okay, that of course cannot be possibly true, because it was noticed in fact by Matthias Eller that if you just do elementary calculation for the original model by using hyperbolic system theory for one dimension, then you obtain the solution, which is a characteristic function of characteristic sector when it's equal 1, when x is equal to 2, and time derivative will be delta function. Clearly, delta function is not equal to 0, which would follow from the approach by changing variables. So here, warning, that's not way to work with a boundary data. There are certain things which we have to be careful. How do we define a solution? I don't know why it's going this way. It's going to me, I don't know why. No, but it's not. Okay, so in fact, Matthias Eller just this year was looking at the problem from point of view of hyperbolic first order system, and he discovers the following peculiarity, that if you write it down, third order equation as a first order system, because this is by introducing additional variables which are kind of a classical, and this is still for my very trivial model, yeah. Then you can write it down on the boundary with respect to x, okay, solving with respect to the normal direction, like we're doing for wave equation, for three variables, u1, u2, and u3, and here it's a first order operator, hyperbolic operator acting on these three variables. But what is peculiar is that there is a coordinate 0 here affecting the third coordinate. So what it means is that this hyperbolic system is characteristic. Okay, wave equation is non-characteristic. Okay, Dirichlet or Neumann is non-characteristic. So here is a peculiarity. So we know that we have to be careful applying theory of hyperbolic systems. I know I have to click on this slide. One more. I know. I don't know what's going on with this.
Click on the slide anywhere.
So here, if it were hyperbolic first order system, okay, which would be characteristic. I don't know what this stupid system is doing to me, you know.
Yeah, not working.
Thanks. Then you would expect the following estimate. Okay, if we could just take from Sakamoto book and read it off, okay, without any work. And what is estimated is similar, analogous to the one for wave equation, that you have a transport of a second derivative on the boundary into the second derivative also here for the solution without any loss due to trace regularity. Okay, that's what it is. That's what was expected. But that would be true for characteristic, for non-characteristic. However, our problem is characteristic and therefore requires special treatment. And that was, in fact, there's a recent preprint by Bucci and Reller, when they prove optimal result for smooth solutions. Okay, so again, feeding H2 boundary data on a boundary, they obtain only normal derivative in H1. They do not obtain the second normal. Okay, and that is not possible because of the characteristicity. So you see there is a peculiarity which is seen that way as well. Okay. Now what we did, we wanted to look at the problem with the rough boundary data, not smooth. And here what was very helpful was a theory of sine and cosine operator and some results which were proved in the past as looking at the singular integrals. And in fact, one obtains, okay, if we take G in L2, one obtains nice results for UT. It's exactly in line like with wave equation. However, second time derivative has deterioration in terms of regularity. Okay, that is exactly related to other way of seeing this characteristic property. And a funny thing is that eventually you try to do obvious thing, as I mentioned, that leads to counterexample, and you don't know where is the error. An error is somehow being commuting this derivative with a Laplacian. Okay, you have to be very careful how do you treat these things for boundary data, as and the G has to be compatible at the origin if it's a smooth solution, and that's what forces you to good model. But the model is here. You have a formulas for the model. This is a model. Okay, so it's not a question what is the definition. Definition is given by this integrals, and so all you have to do just to study regularity of these integrals, resolving the issue. For a more general model, not a simplified, is an analogous thing, and we get a solution as a sort of a variation of parameter with this only G fed by L2. So there are no time derivatives, as you see, but there is also this green element here, which is peculiar to the third order dynamics, okay? And we do, clearly the formula is well defined on G and L2 because this is a operator which is bounded into some dual space, but it is definitely closable on L2 topology. So we can study just regularity of this formula and gives you all the information that you need about the solution. Okay, and that's what led to the final theorem, which shows that if I start with initial data in L2 H-1 and domain of a dual, and G is only in L2, then we obtain solution also continuous L2, velocity H-1, and the second derivative is in a strange space, but a normal first order normal derivative has hidden regularity H-1, but we don't have a second normal, okay? I want to give a couple of references because that was a problem that was looked upon by several people and was started even with Roberto by 2018. There's a paper in SOTA, but he was looking at some a little bit smoother boundary data, assuming continuity. Then Pandolfi approached the problem from point of view of a Volterrine integral equation and obtained also related result. And this is the ultimate model which gives specific optimal results for this thing. And as I said, the tools for proving are really the singular integrals related to sine and cosine operator. But correct definition of the input is very important, okay? Because otherwise we get into the counterexample. Okay, so the last part here, I won't talk about control problem because that was the reason why we are fighting for this good formulation for MGT from the boundary. And in fact, control problem, it's a sort of, I don't know, that people, Barbara Kaltenbacher and Clayson, they wrote a couple of papers, in fact, even for a tau equal to 0 for second order, feeding, because it's exactly the pictures that it's of interest, yeah, in terms of ultrasound application, that we feed boundary data on the boundary and we put an absorbing boundary condition on the other part of the boundary to create some effect of a dissipation. And that was done by this model was considered in the past, okay? And the past result involved some minimization of the functional, which is a minimization of the pressure subject to boundary conditions G, but the G are in a topology of a capital G, which involves a lot of derivatives. Okay, so the here point I want to make, it's a finite horizon problem and very smooth controls when you can do a problem by homogenization. So what? So this is exactly. We have a smooth controls in original paper by Kaltenbach and Clayson. So goal is to do non-smooth controls only L2 and push to time in infinity. If we want to consider infinite horizon, then for this functional and penalize only L2 data, then stability is a critical issue. So how we have to show that this absorption in the boundary gives you stabilizable dynamics, okay? And here is exactly the situation we are looking at. We have a focal point, we have a controls on this, it's important it's convex, I will say why, and then we have some absorbing boundary condition on the other part. And one thing to emphasize that there has to be convexity of the control action. And there is a stability result which is critical for the whole development, and this is joint work with Marcello and Jose, which says that if you start with the initial data, that's a for even nonlinear problem, H2, H1, L2, and we take absorption exactly on this, outside this convex part, on gamma, with some compatibility condition, then we obtain exponentially stable semi-group in the nonlinear case by assuming some smallness of initial data. For linear, of course, we don't need any smallness. Okay, so this results essentially sets a stage for a control problem, and we can, in linear case, we can consider H1, L2 as a topology for doing. And the key part is precisely the correct modeling due to G, which allows to introduce so-called input-output dynamics. Okay, so we write a solution y of t as a sum of three terms. The first one is initial data applied to the semi-group. Then there is this control operators B are control operators are heavily unbounded because they have this Neumann extension, Dirichlet extension, and followed by generator. So you see that these operators are really act on a dual spaces of a generator. That should be A, not a script A. And then we have this integral operator consisting of two parts, and again, very heavily unbounded. So I want to emphasize that the dynamics seems to be very rough. In addition, peculiarity is that initial data, if you take t equals 0, then you don't get necessarily initial data of the system, but you also have a contribution from the control, okay? If you want to determine what happens at t equals 0. That's a peculiarity of the model, but this is exactly the correct definition of the solution and involves only G inner 2, okay? And then we minimize the pressure, which could be written in terms of abstractly some operator R on the dynamics plus L2, okay? So what's important is that this boundary operator are enclosable, and we will be dealing really with the dynamics in domain of A squared dual, okay? Here, resolvent is not compact, so the first coordinate is L2, but the remaining one are definitely distributions. So that's very rough dynamics. And what we want to do on line control. I have to say that there was a result, my joint work with Francesca Bucci, when we are looking at the finite type horizon for this problem, but then it was an additional assumption on control at 0, which kind of made an artificial assumption for mathematical purposes. And it's not really corresponding to the models that we are considering. So we don't want, we need to take a detour from that approach. So what is the final theorem? Final theorem that we have a partial regularity, namely that if we start with initial data, which are very rough, we obtain unique optimal control in L2, capital U is L2, and we get an observation, which is exactly in the right state space. So the transient dynamics is pretty bad. However, we obtain quantities which are originally postulated. And then we obtain existence of Riccati equation, okay, which is a usual self-adjoint positive operator with a strong smoothing properties, because you see here, this is all quite smoothing. So the precisely that allows you to show well-posedness of the feedback. And the reason why we are obtaining this thing is because of this quite peculiar observation of the pressure, and the property like that would be typical for analytic semigroup, but not for hyperbolic. So here we have to really use a specific of the problem. And Riccati equation to obtain is non-standard. Why it is non-standard? The first part is very standard, but you see here, all these quadratic nonlinear terms involve operators which are which come precisely because of the step order dynamics. It's a different structural property. Okay, so people who are perhaps interested in the development of Riccati equation might see, okay, where does it come from? But bottom line is that we obtain a feedback synthesis, which means that we obtain an optimal control G, okay, G star, which is given as your trajectory read online, okay, applied to Riccati operator computed from this equation. And this is operator in front, which you compute, and the regularity is enough to make this well-defined. And there is this G minus 1, so here the question is, you have to show that this operator is invertible. It's not a structural invertibility, but it's a contradiction argument which shows that, in fact, going back to optimization. So we can show. So the final upshot of this is that we have a L2 controlling. You take only information signal at the time t, and you get a well-defined signal to implement into the dynamic. It is exactly the goal of the control. So the conclusion: we solve original problem with L2 rough data. Rough dynamics is in the process, but this is not seen in the final result. We have to solve non-standard Riccati equation, but this can be done by approximation, and we achieve a feedback synthesis on line control, which was a goal. There are several open questions, and of course, this was a model. Feedback control was for linear models, so the next thing is to use that feedback and put in a nonlinear system and see whether it will still provide some suboptimal solution to the nonlinear model. And there are several topological issues here, but it is something to look at And also it would be nice to extend the theory to more general observations. So here we took an observation which was the one coming from physics observation. We want the pressure to be achieved at a certain level, but you can also think of a derivative of a pressure and other quantities. And then some of the ingredients will have to be definitely reworked. And I have here quite a lot of references for you related to the talk, so we might find this thing useful. Yeah. This archive. Yeah. And this is the latest one that we are talking about, the boundary controls joint with Marcello and Roberto. Okay. So thank you very much for your attention. And
Okay, thank you, Irena.
Thank you. Thank you.
So, do you have some questions or comments to Lasiecka?
Oh.
Lasiecka,
Yeah.
have you studied the problem of control from the boundary, controllability?
I tell you what happened with controllability. There is no controllability. The controllability is only partial.
Oh, no controllability.
No, there is no controllability. The reason is that you can see the thing from point of view of certain decompositions, that you have a component of a wave operator that is controllable. But then there is an ODE. And ODE does not propagate any partial derivatives. So you have only partial controllability. So you have to be very careful what is the state you want to control to. So again, there are some papers, that people are trying to do apply methods of wave equation. But here, for example, even unique continuation is not classical. There are results we know how to prove unique continuations. That means that there is some sort of approximate controllability, but it's not a classical one. That depends on this parameter gamma.
Okay, thank you.
So the thing, controllability is, I didn't mention anything, but what one thinks that you ask, okay, we have right now hidden regularity, so can we have a reversibility, like for wave equation?
Even for the interior?
No, for interior, no, I'm talking from the boundary.
Yes, for interior, do you have any results? Did you try?
Not on a portion, unless you put the fully. Not on a portion of it. You cannot propagate from any open set. So even if you put interior controllability but localized, the problem persists. Okay. Okay.
Thank you.
No.
There is a question. Is it please, how can I say to the chat?
Chat. Is there a chat here? Where is it?
Is it possible to construct a Lyapunov functional from the equations obtained at the end? Luis is asking you.
Yeah, okay. The problem, Lyapunov functional, but you want to talk about stability. Because Lyapunov functional, yes.
Yes.
Yeah, for stability is known right now. So stability, it's resolved. Yeah, so we can do stability. Because you see the reason that why this problem does not appear at the stability level, that if you stabilize it from the boundary or from open set, doesn't really matter from the interior. Then you stabilize both wave component, but also your ODE part is exponentially stable to begin with if you put the right assumptions. Okay, so in essence you have a combination of two exponentially stable dynamics. That has to be shown because there is a coupling, and coupling is non-trivial. So, but that yeah, you could do the thing with Lyapunov function as well. But that is not going to help controllability.
Okay, thanks. There is a lot of thanks, Lasiecka, for the nice talk.
Oh yeah, how nice. Yeah.
And a lot of people here. Do you have any other question? If no. Okay, Irena, so thank you very much for
Thanks.
your
Thank you
nice.
very much for having me. It was a great pleasure.